Hi everyone and welcome to my video on the binomial distribution, the final lesson in this part of the course. My name is Darren from Maffs Guru. Yes, Maffs Guru, he says, my little corner there of the interweb where these videos reside with all the rest of the course and downloadable lesson notes and so much more. Please head over there if you would like to, itchy head. Learning objectives behind me, understand what it means to conduct a binomial experiment, understand the ideas of success and failures, very important here. What it means to be a trial, what it means to be a binomial distribution, and how to apply this to a range of probability questions. I think it's going to be a little bit of a long video, and by that probably half an hour, but there is a lot to cover, and it's massive for methods 3 and 4. Now again, don't worry if you are anywhere in the world and don't understand what I mean by methods 3 and 4. The binomial distribution is pretty much universal, so this video could help. Now, as I say, it's the final part. We're going to list up, sort of put together all of the stuff we have done previously. And in the previous video, we looked very much about the idea of with and without replacement and finding various probabilities. And this was the example we used, although I wanted to use Cola cubes. The idea was we've got sort of a jar with toffees and mints in it. And what would the number of ways, if I'm choosing two, of getting a mint? And as we said here over and over again, our sort of outcomes here, our discrete random variable contain the values of 0, 1, or 2. So no mints, 1 mint, or they could both be mints. And we've worked out in the previous video how to do that. Now, for this moment in time and from now on, everything is going to be replaced, all right? And more importantly, there are only going to be two outcomes. It either can happen or it cannot happen. And that's very much what binomial actually means. Now, to sort of scaffold this in a slightly different way, let's look at a spare 6-sided die rolled 3 times. Now, the idea of making a tree diagram for that is already making me sort of break out into a cold sweat. Certainly wouldn't want to do it 4 times, 5 times, 6 times. So there must be another way of being able to do it. And of course there is. But we're going to break it down here, and let's look at the idea as our random variable x is going to be defined as the number of 3s observed. Right, so we're going to let t represent a t and let n represent not a 3. And we're going to consider all the possible outcomes and the probabilities for each outcome. So hopefully you're happy now to be able to read this in terms of, well, there could be 3 t's, all right? So that could be 3 3s. Here we got 2 3s and not a 3. Oh, here we've got 2 3s, not a 3. And here we've got 2 3s, not a 3. Okay. Here we've got a 3 and 2 not 3s. Oh, there's 1 3 and 1 3, and then no 3s. Now, ultimately, what's going to become important here is this idea here. And the idea is, if I was to look at 3 different spaces, and this builds on sort of a previous section of the course, and say, well, what are all the different ways of getting 2 3s? We notice the first 2 could be 3s, and then that would have to not be a 3. We get a 3 first, not a 3, and then a 3. Or we could get not a 3, and a 3. So automatically, there are 3 different ways of getting 2 3s. Now, whenever I do these type of questions, actually, weirdly, I tend to do this type of diagram because it sort of makes sense initially before I scaffold off into the other things here. So our column here says, well, okay then, discrete random variable here has x equals 3, or capital X equals 3, because there's 3 3s. Here, x equals 2, x equals 1, x equals 0. Now, how do we go about working out all of those individual probabilities? Well, I suppose here, when they're all 3s, it's nice and easy, because we know the probability of getting a 3 is 1/6. So a 3 followed by a 3 followed by a 3. There are only one way to get those 3 3s. So a 6 times a 6 times a 6 gives me whatever it gives me. Come to that in a moment. What about this though? What on earth does all this mean? Well, the probability that x equals 2, that means the probability that we're going to get 2 3s in our distribution is given by 3 times 1/6 squared times 5/6. Well, if we go back to my original diagram here, or my original information here, the probability of getting a 3 is a 6th, a 6th, and that's 5/6. So that can be written as 1/6 squared times 5/6. What about the next one? Well, we got 1/6, 5/6, and 1/6. So that can also be written as 1/6 squared times 5/6. And again, what have we got here? 5/6, 1/6, and 1/6. Oh, so it's the same. So basically, I've got this 1, 2, 3 times. So there we go. So there's 3 different ways of getting 2 3s when I throw this 3 times. There are 2 successes, right? Because that's my 1/6 times to the power of 2, and 1 failure. Okay, so now if we were to explore this a little bit deeper, how many different ways are there of getting just 1 3? And again, there appear to be 3 different ways. Here, though, we've got 1 success and 2 failures. So we've got 1 success and 2 failures. And again, there appears to be 3 different ways of doing it. And there we go. That's what we've got here. So we've got the number of ways we can do it, the number of successes to the power of successes. So realistically speaking, we could have written that in brackets to the power of 1. And we've got 2 failures. And here, for no 3s at all, it would have to be 5/6 to the power of 3. Why? Because we've got no 3s, no 3s, and no 3s. Now, when we work out what each of these comes to, we get this table below. And again, this is my probability distribution where there are no 3s, that probability, no 3s, that probability, no 3s, that probability, no 3s, that probability. Beautiful, right? So visually, that sort of makes sense. But surely there must be a quicker way than sort of writing out all of those different combinations to work out how many different I would get. And there's the answer here. Now, again, from a previous part of the course, we know that if I am throwing something 3 times and I'm trying to find the number of ways that 2 of those will meet some sort of success criteria, put my teeth in, will be given by that. So 3C2, which when we turn out and put it into my calculator, we get 3. So let's just check here. This here is 3 rolls, and I want 3 successes, right? So when we're talking about the number of tails, we want 3 rolls and 3 tails. Here, I want 3 rolls and 2 tails, 3 rolls and 1 tail, 3 rolls and 0 tails. Now again, when I put those into my calculator, lo and behold, that comes out as 1, that comes out as 3, that comes out as 3, and that comes out as 1. So that 3 there is because of that 3 there is because of that, and basically the rest of this I'll explain hopefully in a little bit longer. So the idea of combinatorics is really, really important. This formula here is really the one that needs to go in your summary book, and it can be written in one of 2 ways. So to break it down, this nx in brackets is nothing more than saying for, he says, a certain number of trials, how many ways are there of getting a certain number of successes, where R is the number of successes, right? So NCR, then we got this P to the power of X, all right? Now, I don't know why I put R in there for some reason. That should be X. I've got NCR for my calculator. Now, whatever the number of successes here, that's going to have that power of successes. So again, if we were looking previously, 3 throws, I want 2 3s. Well, the probability of throwing a 3 was a 6th, and I wanted 2 of them. So what's the next section? Well, where did this come from? 1 minus P. Well, binomial deals with successes and failures. If it's not a success, it's a failure. The probability of getting a 3 was 1/6, so the probability of not getting a 3 must be 5/6. So that then became 5/6. And again, I normally put that in brackets because if I've got 2 successes, I must therefore have 1 failure, and in this case, not a 3. And that effectively is what this formula is trying to build up. And yes, I can go back in a minute. Well, let's just go back now. And let's look, and again, that's where that came from. 3, that was 3C2, 2 successes, and 1 failure. Now again, this becomes hugely important in questions like here, for example, rainfall records on the city of Melbourne indicate that, on average, the probability of rain falling in any one day is 0.4. Now, decoding these questions is what tends to throw students left, right, and center. Because rain, it's either going to rain or it isn't going to rain, I can look at this question now and go, oh, binomial, yes. And in which case, I now know that my P, my probability of success, is going to be 0.4, and my probability of not having a success is going to be 0.6. Why? They have to add to 1. Assuming that the occurrence of rain on any day is independent of whether or not rain falls on another day, and important conditions for binomial, find the probability that rain will fall on any 3 days in a chosen week. Okay, so we want the rain to fall on 3 days. So the first thing to do is say, well, how many days in a week? There are 7. Choose 3. So out of that 7 days, how many different ways are there of me choosing 3 of those for rain? And again, if I was going to draw this out, 1, 2, 3, 4, 5, 6, 7, it could rain, 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 not rain, not rain, not rain, and not rain. That's one of those different combinations. And if you think about all the different ways now, we can arrange these R's so they fill and completely different arrangements each time. That's effectively what this is doing for us. A lot quicker than me drawing all of that out. So 7C3, this is following my formula, times by P, the probability of success. So we want 3 days where it's going to rain. Well, if it rains on 3 days, it can't rain on 4 of those days, yes? So fundamentally, the rain will fall. And again, what we tend to notice is that value there is the sum of those two there. This here is the same as that one there, right? So now, if I want to, I can fire up my calculator. He says doing Desmos again every single time. And so what I can now do is NCR. I know I can just type that on my calculator. It's going to be quicker than doing the 7,3 times 0.4 to the power of 3 times 0.6 to the power of 4. Are we happy with that? And there we go. So the probability that it is going to rain on any 3 of those days would be given by 0.2903. Now, in most cases in methods, they will ask you to do decimals to 4 decimal places. I don't know why it seems to be a convention. All right, now there is another way of being able to do this, and basically your CAS has this information for you. And again, sorry for the ClassPad guys, your calculator has very similar functionality, and I only tend to show the ClassPad when it is massively different. But here we are looking for our sort of binomial PDF function in my CAS. There we go, there's my binomial PDF, A. It's under probability distributions and A, and it brings up this beautiful dialog box. And again, it only wants 3 pieces of information. The number of trials, all right, so how many times you're doing it. And in this situation, we'd probably want that to be 7. The probability of success, 0.4, and the X value. Now, you'll notice the X value says optional. We'll come back to that, why that is in a moment. But in this situation, because we want a specific number of days it's going to rain, we can say 3. There we go. So if I put that into my calculator, 7.43, lo and behold, out comes what we were expecting. There we go, 0.290304. So again, much easier to use that than be faffing around with that formula even. So knowing how to use your calculator, it's even better. Another example. For the situation described in the previous example, use a CAS calculator to find the probability that rain will fall on any 3 days in a chosen week. Rain will fall on no more than 3 days of a chosen week, and rain will fall on at least 3 days of a chosen week. And again, the language here is what tends to trip people up. No more than, at least, and on any. So there is an inequality being talked about here. And again, when you break that inequality down, this one here, probability that x equals 3. I think we've already done that. X is less than or equal to 3. And rain will fall on x is greater than or equal to 3. Now, again, using the CAS is really important. This one here is binom CDF. You want one specific probability for one specific case, then you do binomial CDF. But what about the inequality ones? Wouldn't it be great if there was a way to use your inequality ones? Well, firing up my calculator, if I actually go menu, probability, distributions, and then binomial, scroll down, there's actually this binomial CDF. That basically means cumulative. Can we take a range of different probabilities from these tables and add them all together? So I'm going to hit binomial CDF. And again, we've now got an extra sort of column. It says number of trials N. So the number of trials is 7. So basically I'm going to look at this example here for the moment. So the number of trials is going to be 7. Probability of success is 0.4. Lower bound. Well, because we're looking for the probabilities that are less than or equal to 3, we're looking to take the probability of 0, probability of 1, probability of 2, probability of 3, and add those all together. So my lower bound is actually 0. My upper bound in that situation would be 3. And when I hit enter, he says my calculator's not working, and I'll turn that off again. 0.710208. So there we go. Again, just by using now a binomial CDF, I can get a range of probabilities and add them together. What about x is greater than or equal to 3? Well, again, my binomial CDF, if I bring that up and do it again, menu, probability, distributions, and then B. My number of trials is 7. Probability of success is 0.4. Now my lower bound is actually going to be 3 because I want to add together 3, 4, 5, 6, and 7. So 3, my upper bound is 7, hit OK, and there we go, we get 0.5800, which is the right answer. Again, the CAS makes life so much easier. Now we can also see what the distribution looks like. For any particular binomial distribution, we can see what it looks like. So imagining here, we've got an example where we've got the number of trials is 8 and the probability of success is 0.2. Now you'll notice a moment ago, I turned around and said, well, that binomial PDF, where do we have the binomial? Let's go menu, probability, distributions, binomial PDF. Number of trials. Well, in this situation, I'm going to do 8. Probability of success is 0.2. And that value of x said optional. So if I now hit enter twice, what we now get on our calculator is all the individual probabilities for that table. This has actually worked out. So really, this is like now filling out my x values of 0, 1, 2, 3, all the way up to 8. And my PR x equals x. And my first value is going to be 0.17 and then 0.34. And so all of my individual probabilities are going to be built up. Now, if you look at the screenshot, the way that we have to do with this is, in the CAS is to actually now sort of store that in a sort of variable, and we've called it PR. So in that situation, I've stored those variables in PR. And then what I need to do is if I effectively try and sketch that, let's just do that now. So I'm going to do this, and I'm going to store it, he says. So I'm going to go Control, Store, PR, hit enter. Now, if I go and insert a list and spreadsheet, control doc, data and statistics is what I meant. You'll notice there it's just put all of those random numbers on there, and I've got sort of scientific notation, yuck, 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 but that's fine. But how am I actually going to plot each of those probabilities? You know, you've got to have two things in which to sort of plot it against. Well, as it turns out, we can now suggest, or we can use our calculator to, oh, that's awkward. I didn't have my calculator on. There you go. I've just basically put on my calculator. All right. What we can now do is I can store the numbers 0 to 8 in my calculator. And because we need to have those values along the bottom. Yeah. So if I bring my calculator back up, so this time you can see it, I'm going to do a set of curly brackets. I'm going to do 0, 1, 2, 3, 4, 5, 6, 7, and 8. And I'm going to go Control, Store, and let's call those in my values of x. Back to my list and spreadsheet, and I now go x here, and I do PR up there. Ooh, pretty animation, right? And now, if I think I go here, there you go. We got pretty much the same thing. So that is going to be my binomial distribution with 8 data items with a probability of 0.2 or probability of success 0.2. And you'll notice it starts to do that. Bell curves, all of that coming up with VCE, etc. But it's an interesting way of being able to do it. One of the trickier types of questions that VCAA or VCAA or your examiners try to put on are these type of questions here. The probability of a winning prize in a game of a chance is 0.2. Okay, that's important to me. Highlight that. That's my P equals 0.25. Sorry, I said 0.2. What is the least number of games that must be played to ensure the probability of winning at least twice is more than 0.9? Huh? Well, what you'll notice now is they've not given you the number of successes. They want you to find the number of successes. And they've told you the probability has to be greater than 0.9. Now, again, this is a bit of a head mess, if you were. But what we tend to do is we say, well, what we're looking for then is the probability that x is greater than 2, that there are, 2, 3, 4, 5, onwards successes being greater than 0.9. Well, we can't find that. That would be crazy. But what we can actually do is therefore say, just turning the logic on its head, that if I've got my table with the value 0, 1, 2, 3, all the way up to n, if I know that I add all of these probabilities together and it's got to be greater than 0.9, that means that these two probabilities here have to be less than 0.1. So I can actually say the probability that x is less than 2 would have to be less than 0.1. Okay, how does that help us? Well, I know the probability that x is less than 2 is made up as the probability of x equals 0 plus the probability of x equals 1. How does that help us? Well, we know how to find probabilities of x equals 0 because we can go back to that formula we put in our formula book, which is going to be nc0. And you're going to say, but we don't know what n is. That's okay. That's not a problem. So here, writing it in a different way, nc0, 0.25 to the power of 0, 0.75 to what? Well, that's going to be to the power of n. The reason we like this is if you go back to your understanding of what nc0 means, anything with a c0 is actually going to be equal to 1. Anything to the power of 0 is going to be equal to 1. So this here is actually just equal to 0.75 to the power of n. Ah, what about this? Well, that would be written otherwise as nc1, 0.25 to the power of 1, 0.75, and in this situation, n minus 1. Because if you remember, whatever this is, subtracted that gives me this. Well, again, what is nc1 going to be? Well, we know that anything with nc1 is going to be n. That's going to be 0.25. And that's going to be 0.75 to the power of n minus 1. All right, okay, so that's what we've got here. When I add those probabilities together, so when we take this one here and we add it to that one there, we know that we are looking for a value of n that comes out to give me less than 0.1. Having done the algebra, I can change this now into 0.75 to the n, this into here. And what do? We have a calculator. And so I simply solve, including, he says, the probability. Now I'm actually going to stop that for a moment because I didn't put the inequality sign in here. And I think there was a reason. I don't think it worked with the inequality sign. So I think I had to check it for equal to 0.1. And then it gave me that the n came out as minus 2.86 times. Yeah, automatically discount that. Or n of 14.0421. Now, again, we can't write 14.0421 times. What we then have to do is think to ourselves and go, oh, well, okay, then 14.041 times will give me 0.1. I want it to be smaller. I need to go to one value bigger. And lo and behold, out comes my answer of, I believe it's going to be 15. All right, so bear with me a moment. All right, so actually it's going to be 15. What I do on this screen is I actually just check, because if I'm not sure about, is it going to be 14 or 15, what I did then was went back and put the values into my calculator, and I said, well, okay, if I do a binomial CDF of 14, n equals 14, 0.25, and 2 all the way up to 14, I actually get a cumulative probability of 0.899. Well, that's actually not greater than the 0.90. So again, I tested it with 15, and out came my cumulative probability of 0.9191. Now I'm going to pause for a second because I went on a conference really, and this blew my mind once again because I was like, hold on a moment, he's just shown me a really easy way to do this in my calculator. So I'm actually going to go back to here, and I'm going to show you that there is a function when you go menu, probability, distributions, and you scroll all the way down, he says, to inverse binomial n. Now, the reason it's doing that is it actually can work this out for you with nothing more than a simple screen here. Now, it can't actually do more than. So, although the question was framed again as the probability that x is greater than 2 is greater than 0.9, you have to go, well, okay, the x is less than 2 is less than 0.1. And so you actually put that information here. So what is my cumulative probability? Well, the first thing it says, it wants my cumulative probability to be 0.1. All right. It wants my probability of success, what did we say, to be 0.25? And the number of successes, now that's got to be up to and including, not 2. In this case, it's going to be 1. I don't worry about matrix form. I'm just going to put equal, and lo and behold, can you believe that that value there comes out to be 15? Ka-ching. One calculator function, saving all that hard work. And again, there are other ways of doing this. You can actually graph these things and come up with tables and whatever else. I'm going to leave that to my year 12 video. Right, what do we get here? The probability of an archer obtaining a maximum score with a shot of 0.4. Find the probability that out of 5 shots, the archer obtains a maximum score 3 times. All right, so we've got my probability of success is equal to 0.4. And find the probability that out of 5 shots, n is going to be 5. The archer obtains the maximum score 3 times. So we're looking for the probability that x equals 3 is going to be 5c3, 0.4 to the 3, and 0.6 to the power of 2. If we were going to do it the long way, and let's do it the long way. We love doing things the long way in maths. So let's just see what happens here. So that's NCR 5,3 times 0.4 to the power of 3, was that? Yep, and 0.6 to the power of 2. Hit enter, and out comes 0.2304. 0.2304. I'm going to check that on my calculator with the menu, probability, distributions, binomial, what do we want? CDF? No, PDF for one value. Number of trials, 5. Probability of success, 0.4. X value 3. Hit enter and hit enter again. And 0.2304. There we go. Cool. Love it. Now, we then get to conditional probability. So we now want 3 times given that she obtains a maximum score at least once. All right, so we're now looking for the probability that x equals 3, given that x is greater than or equal to 1. Right, so in which case that's going to be the probability that x is equal to 3 and x is greater than or equal to 1, divided by my probability that x is greater than or equal to 1. Well, in this situation, it seems fairly clear that these are overlapped because, you know, for x to be 3, it is over 1. So therefore, that becomes the probability that x equals 3. Thank you very much for scaffolding my previous answer. So it's going to be 0.2304. X is greater than or equal to 1. How am I going to work that out? Oh, I think I've got a tool to be able to do that. Menu, probability, distributions, binomial CDF. Number of trials we said was 5. The probability of success was 0.4. The lower bound in this situation was going to be 1. Upper bound was going to be 5. Hit enter, and we get divided by, and again, we'll just write that in longhand. X is greater than or equal to 1. 0.92224. And so therefore, doing that divided by that, hit enter, gives me 0.249 and 8. And I'm going to put it to 4 decimal places because, again, pretty much it's asked to be in 4 decimal places in VCAA papers. And that's something to also be very aware of at the start of the exam to make sure that you sort of read the front cover and sort of understand what the order of accuracy is going to be. Right, we're done. So, have we understood what it means to conduct a binomial experiment? Yes, because that's something with an either, success or a failure. That's it. Understand the idea of successes and failures? Yep. Understand what it means to be a trial? That's just one outcome. Understand what it means to be a binomial distribution? We've looked at that and know how to apply that to lots of different questions. Thank you very much. Hopefully the video has been good. If you can subscribe to my YouTube channel, I will be so pleased. It just tells me you've been watching, really. Spread the word if you found this useful. But I'm done, I think, for this particular section of the work. Let's record some more videos a little bit later on. Hopefully I'll see you again. Remember, maffsguru.com for all of this information. Until next time, take care. Bye-bye.